In modern high-power density applications, the liquid cold plate has become a key technology. It is not only the core cooling component for electric vehicle battery packs and AI servers, but also increasingly takes on the heavy responsibility of structural support. A successful cold plate must find a delicate balance between cooling performance, mechanical strength, long-term reliability, and cost-effectiveness. To achieve this, a rigorous engineering framework covering design, manufacturing, and verification is needed. This video will analyze the complete journey of a high-performance liquid cold plate from the design blueprint to the final product. Phase 1. Design and simulation. Everything starts with a precise understanding of customer needs. The design process is not just simple size matching. It is an optimization process driven by simulation. First, we define the requirements. We start with the customer's core needs: heat power, heat source location, installation space, and load-bearing requirements. At the same time, fluid parameters, such as the coolant type, inlet temperature, flow rate, and allowed pressure drop, form the boundaries of the design. We optimize designs by balancing fundamental engineering with advanced simulation. While we fast-track mature concepts using established heuristics, we reserve rigorous CFD and structural validation for high-demand challenges. Simulations highlight initial thermal weaknesses, enabling us to optimize geometries and present a distinctly superior final performance comparison. Finally, material selection. Aluminum alloys are the mainstream choice. The 3000 series, like 3003, is great for brazing and is the top choice for stamping. The 6000 series, like 6061 and 6063, possesses higher strength, making it ideal for load-bearing parts. Phase 2. Forming processes. Once the design is ready, choosing the most suitable manufacturing process is key to turning it into a physical object. Option 1. Stamping. This is the mainstream process for mass production, suitable for prismatic and pouch batteries. With widths ranging from 30 mm to 1,900 mm and lengths up to 2,600 mm. Using large presses, we shape the aluminum sheet into a half plate with channels, then weld two halves together. The cycle time is extremely short, about 30 seconds, making it very cost-effective. It also offers high design freedom for complex paths. Option 2. Extrusion. This process pushes heated aluminum through a die to form profiles with complex microchannels in one go. These are single-piece structures with high body strength, perfect for side cooling plates that need to bear weight. While the cooling effect is excellent, the width is usually limited to 300 mm due to equipment limits. Option 3. CNC machining. This involves milling the flow channels directly from a metal block. It requires no molds and offers the highest design freedom. It is the best choice for prototypes or small batches, although the cost per unit is higher. Phase 3. Precision welding. The formed components must be sealed into a whole unit using highly reliable welding technology. Option 1. Furnace brazing. This is the most common method for stamped plates. The parts are heated in a vacuum or nitrogen furnace to fuse the plates together. Automated lines ensure high consistency for mass production. Option 2. Friction stir welding, or FSW. This is an advanced solid-state technology that connects metals by physical stirring without melting them. The weld strength is almost equal to the base material, eliminating defects like pores. It is the preferred solution for high-reliability applications. Option 3. High-frequency welding. This uses electromagnetic fields for instant local heating. The heat-affected zone is very small, keeping the material strong. It is especially suitable for welding extruded profiles where precision is critical. Phase 4. Surface treatment and final verification. The final stage before delivery is to perfect the product's functionality and pass strict tests. First, surface treatment. Depending on the environment, we might use anodizing to enhance corrosion resistance or powder coating to provide extra physical protection and insulation capabilities. Second, strict quality inspection. To ensure long-term reliability, every cold plate must pass airtightness testing. We run helium or pressure holding tests to verify leak tightness and minimize risks. We also use precision instruments to check key dimensions and flatness. Finally, we use non-destructive testing, like X-ray or ultrasound, to check the welds for any internal defects, ensuring the integrity of the structure. The birth of a high-performance liquid cold plate is a system engineering project that integrates thermodynamics, materials science, precision machining, and automation control. From the initial simulation design to the choice of diverse forming and welding processes, and finally to comprehensive quality verification, Every link is crucial. Understanding this complete process helps you make smarter technical decisions. It is the solid foundation for choosing a reliable partner who can provide full process technical support from design to mass production.